Hello everyone, my name is Anthony Shivkumar, and in today's video I want to simulate the characteristics of a MOSFET. Now, in this picture that I have over here is basically a very high level graphic of what is under the drone. You have a drone and then you have, say, propellers to allow the drone to fly. And to control the propellers, you have an electronic speed controller that controls the speed of the propellers. And when you dive deep into the electronic speed controller, at the heart of it, there are a couple of MOSFETs that are switching. And when you're working with a drone and you look at the whole system, you really want to select components and devices that fit well into the whole drone as such. You want to make sure that the electronic speed controller is optimized for your drone. You want to make sure the propellers are optimized for the electronic speed controller, and the electronic speed controller is optimized for the drones. And the drone could have various shapes. You could have a quadcopter, you could have an octocopter, you could have even a bicopter, it could be a helicopter. And based on your configuration, the mechanical consideration, the physical constraints, you want your electronics and your hardware to work in harmony. And at the heart of it is MOSFETs. And understanding the MOSFET at a deeper level, understanding, what are the switching losses, what kind of MOSFET to select, what are the characteristics of the MOSFET, how much heat is it going to generate, whether it's going to blow up or not. Is it able to control the propellers at high speed? What power is it going to, can it handle before it blows up? And all those things helps you select the best electronic speed controller. Or if you're designing your own speed controller, which is pretty much what this channel is all about, building up things from the ground up rather than buying something off the shelf, you want to have a deeper understanding of the components that go inside an electronic speed controller. And in this case, it's the MOSFET. So I've selected a few MOSFETs, and in this particular video, we're going to dive deep into the characteristics of this MOSFET, understanding, what are the switching characteristics, how much power is dissipated, and all the different parameters that a data sheet that the MOSFET manufacturer would give you in terms of what the data sheet is trying to tell you and how do you make sense of it. That's really what it is. Now, what I have over here is basically, I'm yet to fabricate this board. This will be another video where I'll do the physical experiments. But what I have over here is a MOSFET over here. And I'm going to basically try to find the characteristics of this MOSFET from the data sheet. And we'll see what the manufacturer provides and gives us. So all I'm going to do is, So what we have over here is the PSM1R225YLD, and it's an N-channel MOSFET. It can handle 25 volts, and the packaging is the LPFK56, which is basically what I have in here. This is the packaging. And I've used this particular MOSFET to design various different speed controllers, and I found this to be a MOSFET that can help in designing and working with electronic speed controllers, because it can handle high voltage and high currents. This will definitely fit within the a 3S battery pack, which is 25 volts, which is way within the 12 point or 13 point voltage range that a 3S battery would provide. And the current that this can handle is quite a lot actually. So it's 230 amps. So you most likely it's way beyond its capacity. It's way beyond what you would need for an electronic speed control, especially for a hobby level drone or even a small level drone. So it's a very capable MOSFET for an application that we want to build. And in here, when you go to the manufacturer, you go to the documents, there'll be different types of documents that they provide. So what we're really interested in the two things. One is the data sheet, which I've already pulled up over here. Let me just bring that out. And the second thing is the SPICE model. The SPICE model gives us information into how we can simulate different working conditions, derive whether the MOSFET fits your application, and understand it at a deeper level whilst using simulation tools. And from there, you can select whether this MOSFET is right for you, and if it's not, select a different MOSFET. So that's what we're going to use. We're going to use the SPICE model that's provided by this particular MOSFET manufacturer. So what I've done is I've downloaded the PSM1R2 SPICE model, and I have, just give me a minute, imported this into MATLAB. And I'm using MATLAB for this particular case. It doesn't matter, you can use any SPICE tool, but since I'm getting a little bit more mathematical in here, I thought this was a better tool to use. But as I mentioned, it really doesn't matter what SPICE model, what SPICE tool you want to use. You can use an actual, things like LT SPICE. You could even import it to things like PSpice, Cadence, ADS, whichever is your SPICE tool of choice. And there are a sequence of steps to convert a SPICE model to a simscapes model, and if you just follow this syntax over here, you can use the subcircuit to sec, and then from there you basically, once you create the file, then you can basically create from the subcircuit array, you create the library, and from there it'll create the Simulink model. So I've gone through the steps of downloading the file from the manufacturer and then using the converter tool in MATLAB to convert this into a Simulink model. And what I have over here is, let me just open it up, is my Simulink model. Now I based this on the EE_MOSFET characteristic of MATLAB, and I've just modified it to fit this model over here. So this is the PSM1R2 25YLD. And once I brought this into MATLAB with the SPICE configuration that the manufacturer is giving you, you can do a lot of the simulation, play around with the resistor value, play around with all the different parameters to make sense of it. And that's really what this video is all about. And we can look at the data sheet to make sense of, what's really happening under the hood. So what I have over here, I've got all these tabs open. So what we have over here is I'm going to look into the different characteristics of this MOSFET and just do a simple simulation. And let's understand what this circuit does. So we have a MOSFET over here, which is the PSM1R2. It's got drain, gate, and source, and the drain is connected to a voltage source. Over here we have VDS max. VDS max is 12 volts. So if I look into my thing over here, it's 12 volts, or 12. And here it converts it into a voltage source. And here we have a drain current sensing, and it goes to the drain. And from the source, we have connected a MOSFET, which has VDS max, which is 12 volts divided by 100. And I'm playing around with these parameters to see, how the characteristics of this MOSFET changes. And we're giving it a pulse voltage input. So it's 1 second is the period, and the pulse width is going to be 0.5 seconds. So that's basically after every 500 milliseconds, it's going to turn on, and 500 milliseconds is going to turn off, and this keeps repeating. So we're basically trying to simulate a switching phenomena over here. Now mind you, this does not really simulate exactly what the switching speed when you're trying to control an electronic speed controller, but just for the sake of this particular demonstration in video, just to understand the characteristics, I'm making it one second. The switching speed would be at least 10 kilohertz to 20 kilohertz. So that's going to be that many, 1 divided by 20 kilohertz. That's the seconds that we should be actually working with. But in this particular case, I'm just making it generous with the time. And then what we have over here is a voltage to drain source. This is just a simple scope that I've added to check the drain and source voltage. A lot of this we don't need to actually measure, because there is something that the Simulink or the simscape system already allows us to identify, and it does a lot of the scoping for us. So I'm going to now start to simulate this particular circuit. And once the circuit is simulated, I'm just going to close all these graphs so that we can see everything from the grounds up. And let's look at the plot results of the curve. And this is a way of basically saying that if I keep increasing the gate voltage, how much current can flow from the drain and source. So MOSFET, this is not a basic video on how MOSFETs work. So if in a simple sense, like if you increase the gate voltage, the amount of current that can flow from drain to source will automatically increase till you reach a resistive value, or ohmic region, which they call, which is basically you're pretty much turned on the MOSFET, and it's got least amount of resistance, and it's turned on. But before it turns on, it does not always, it's not always a linear what do you say, output. Okay, I'm having some errors over here. Let me just check what we have over here. 0.5 vector gate. Do I have to? Yeah, it's 0 to 0.5. Just gonna expand this a little bit. yeah, this looks okay. And we have over here, just thought I'll just basically define test minimum drain source, maximum drain current. Oh, okay. So yeah, so one thing I'll just do is I'm just to get the just to get this particular graph working, I'm just going to put a ramp over here, and the ramp is going to sample the graph at very specific voltage levels. So this should work, I think. Or there should be a constant voltage. What we'll do is I'll show you the example from MATLAB, and it'll basically give us the characteristics of this graph. So what we're trying to simulate is this particular graph over here. So when we go into the MOSFET characteristics, it will show you the different ways in which this turns on. So basically you're having a drain to source voltage, and here's your current. So let me show you what I mean by this. Now, yeah, this is not coming out particularly well. So the red is at 10 amps because 10, that's what we have over here. So it's in a simple English, it's basically turning on. It's taking some time to turn on, and then it turns off. And this is because we're basically having a turn on of 50% duty cycle high and 50% of duty cycle low. So this is basically the turn on of the drain current. Ideally, it would give you this particular graph, but because I'm pulsing it over here, it's not the perfect perfect schematic to represent that particular voltage. So what I'm going to do is I'm just going to give this basically a voltage source. Just put here and click here voltage source, and in here I'm going to put in, say, it's a setting. Just actually check the so I'm just going to go to MATLAB EE underscore MOSFET. There is the demo thing that you could use, which is called the EE MOSFET thing that I basically modeled on. And here you have the plus minus VG, and what we'll do is have a look at what that does. So what I'm going to do is open the actual MATLAB. For that I need to be in another folder, and I'm just going to do, say, EE underscore MOSFET. We'll just copy that particular voltage source in here, and yeah, that's fine. Okay, let me just go in here. Yeah, I just need to basically be in another folder kind of a thing. And just put here. It's constantly opening this particular thing. Let's try to simulate this. Yeah, so it's giving me the error because I'm in the wrong path. What I'm going to do is go back to where I was. This is the MOSFET. Then we'll just simulate this. See if this works. Yeah, it's not showing me the right so this is the drain current, and yeah, this is super small, so it's I'm missing a parameter over here. what I'm going to do is as I mentioned, it should supposed to basically simulate something of this sort, and it'll give you a graph like this. And in here you're supposed to use the right voltage source. Normally I would just take this model and use it, but in this particular case, so what I'm going to do is I'm going to save this, and I'm going to close this particular thing and then open the real model. So what I'm going to do is go to a different folder, say over here, and then just to get a sense of what that is. And this is the MATLAB version. So if you run this, and then you can click the plot graph. So I'm just going to copy this VG source. So many parameters. I'm rather just copy it from the demo version rather than redo the whole thing. And here's the graph. So this is of their version of the MOSFET. So we want to replicate this graph for our MOSFET. So what they're using over here is it's just a DC voltage source. So I'm just going to copy this because that's what's missing in what we have over here. And I'm going to go back to our directory and basically open what we have, which is the EE MOSFET. Might have to close this. Let me see if this opens up actually. And it's, yeah, so this is where it gets tricky. So I'm just gonna click nope, and then I'm gonna click this again. Okay, and I'm gonna use this voltage source over here that we have. So I'm just going to remove this and then place this over here, and then we run this, and then I'm going to simulate this, the plot results. I believe it should work. Yeah, it's taking some time. I have added a lot more voltage. Yeah, there we go. Perfect. Okay, so so this is basically I've added a lot more, and the reason being is because so this is the characteristics of this particular MOSFET, and as you can see, as you start to increase the gate source voltage, it starts to increase. This is looking super good. And if you look over here, you can see that this is the graph that we're trying to basically simulate over here. And does it match, what this the actual data sheet is providing? And we're trying to simulate this. So at 2.4 volts, you're generating, you don't have that much amps, maybe around like less than 10, So over here we only have from 0 to 30. So this green one, so 0 is going to be 0. Then at 0.5, you're looking at, 2 amps, 3 amps, 4 amps, till you come to 5 amps. And the blue one is around 2. So 2.4 is the red one, and that's around here, you could say. So this is the 2.4, this is the 2.4 VG, and over here we're looking at 5 to 6 amps around, at it'll be around 6 amps of current that can flow, and after that it's not completely turned on. And you can see that it's approximately at this level, say this is 20, then this would be 10, approximately 6 amps. So you're simulating this, and of course this is going from 0 to 200 amps, whereas over here we're just going from 0 to 30 amps. So it's a little bit more granular, a little bit more zoomed in. And this is a good graph because it's allowing us to understand the characteristics of this particular MOSFET, and it's different for every MOSFET. And does this work for you? So, if I given 2.5 amps at 2.5 volts at the gate, I'm only going to get around 6 amps of current flowing through, and there's going to be a lot of resistance. And as I increase it to like 10 amps, which is approximately the last one over here, you can start to see that it's starting to get into the ohmic region. And at 10 amps, it's so if I bring this graph back again, where is 10 amps? So at 10 volts rather, you're looking at it's starting to go in this graph. Now, of course, you zoom in from 0 to 200, it's pretty much a straight line. But when you zoom in from 0 to 30, you can see the gradual, like there's still resistance. And if you increase the gate voltage to more than 10 amps, probably 20, let's put a 20 over here. So what I'm going to do is go over here to define test, and we'll just do a 20 because that's the maximum capacity of the what are we doing over here? So I'm just going to go over here and put in a last one of 20. Let's put this over here. So this tells me when I am creating my ESC, my electronic speed controller, this graph tells me at what voltage should I be applying to the gate of this MOSFET so that I can minimize resistance when it's switching. That's what we're really getting at over here. And we're switching 6 MOSFETs to control a simple brushless DC motor. And you really want it to be conducting and having less amount of power dissipation or losses. And you can minimize that loss by increasing the gate voltage. And that's why this graph is so important, because this directly relates to the MOSFET you're selecting and whether this MOSFET is appropriate for your use case. And if it is, you want to know what voltage you want to hit your gate so that you're minimizing the resistance. So that's why this is such an important basic characteristics that you want to analyze before you select a MOSFET. And here we go, and you can now see that between the 10 volt gate voltage and the 20 volt gate voltage there's very little difference, at least till you're drawing 30 amps. Now, of course, if you're growing more than 30 amps, which you can see over here in this particular graph from the data sheet. So if you're going, this is 10 amps is pretty much almost straight, but if you go for 20 amps, it'll be a little bit more ohmic. There's still resistance, but it's significantly less. And there's not much difference from 0 to 30 amps when you're dealing with a gate voltage of, from 10 volts to 20 volts. It's if you're drawing more current, getting into the 100 amps to 200 amps, then the difference probably might be a little bit more. But for our electronic speed controller, you're most likely not going to cross more than, at least not frequently, you're not going to have more than, 30 to 60 amps at most. So that's one characteristic that would be super useful if you want to understand the characteristics of this graph. So I'm just going to, dock it over here. The next thing that we're going to do is now pulse this thing. So I have two different things. So all I'm going to do is just exchange this with from a ramp to, and I'm going to take this pulse. So that matches the data sheet. That's something that, it's a good way to simulate to see whether you got the right model and it's matching what the data sheet tells you. Now you would also want to conduct the actual experiment, because the data sheet may be, all they've done is basically simulate the SPICE model, and not a good idea. So what I'm going to do is again run this. And this time what we have is a pulse. And the pulse is basically going to be a 50% duty cycle and for 1 second. And then we have a resistance. And what I'm going to do is explore the simulation results over here. And this is the simscape simulation that basically helps us understand every aspect of the MOSFET. And we're just going to explore it. Here we go. And it'll bring up this toolbox. And this is, basically helping you understand what's happening over here. So if I go to the gate voltage, I'm turning it on. for half a second, and I'm turning it off for half a second. This basically tells me the source voltage. The source voltage is going from 0 ohms to 0 volts to minus 500 volts. I don't completely understand this, so we'll look into this shortly. The drain over here is at 4 volts. Okay, so basically I think I have not run the simulation properly, because this is definitely not 4 volts. VDS max is, how much is VDS max? We have VDS max is 4 volts. We'll put this at 12 volts actually. So this in my opinion should be maximum drain source voltage. Yeah, it's 12 volts. That's VDS. So in here, let's put this as 12 volts. I don't think I should be changing it this way, but I'm just going to open this sheet, put this as 12, close this, and run this. Or it could also be even 10 volts actually. Yeah, this could be 10 volts, and here we have it at 5 volts. And here actually I would basically put this from 0 to peak value of V2, maybe put this as 10, so that, as we've seen, we can get a lot more, least amount of resistance. Simulate this, explore the simulation results in simscape, and let's have a look right now. Okay, and what I have over here is the drain voltage is 12 volts. That looks right to me. The gate voltage is pulsing between 10 and 12, and here we have a source voltage, which is making a lot more sense. That is going from, that's around 7 to 7.5 volts because of the voltage drop, because of the resistance. That's making a lot more sense to me. So let's look at the resistance. The resistor is, we have a resistor over here, and here we basically had this as 12 divided by 100 is 0.012. And in here we're looking at the amount of current that is flowing through it. So you got around 60 amps, which is a lot, as you can see. And that's basically telling you that we're basically turned on the MOSFET pretty at its full level. So what I'm going to do is reduce the I'm just going to go over here and reduce this. Instead of putting this at 100, let's put this at, say, 25. Hopefully we can get this at 25 amps then. If I run this, and then if I simulate this once again, and if I go to the resistor, and then let's look at the resistance. And here we're looking at it, it peaks at 25 amps, and then it goes to 15 to 16 amps over here. And why is this important? Because what I'm trying to show you over here is that there is something called as the say the gate source plateau voltage, and it basically says that actually there's a lot more other variables over here, but what I'm trying to get at is if I give in a drain to source voltage of 12 volts, and if I basically give it at 25 amps that I need for it to pass through, at 2.7 volts, which is a plateau voltage, which is very little drain source, that's where you'll basically have this plateau. And we can look at figure 12 and figure 13. And a plateau is basically saying that the gate does not immediately turn on. It turns to a certain threshold, then it stays there for a little bit of time, and then it goes, then it completely turns on. So that's basically what a plateau of a MOSFET is. Figure 12 and figure 13. So this is 8, 9, 10, this is 11, this is 12. So you can see that it goes to a certain level. Gate source voltage is a function of gate charge. So this is the gate source voltage. So it'll go to 2.4 or 2.8, and then it turns on before it goes to 10 volts. That's what this particular MOSFET characteristic is. And even stage 30, and even this particular graph tells you that it's going from gate source voltage, it reaches a plateau, and then it turns on. And this time is based on the charge of present at the MOSFET, and it's a dynamic thing. It changes according, based on the amount of voltage. So these are just dynamic variables. So you got basically the charge of the gate and source plus the charge of the gate and drain. That is the time it takes for the voltage to go from 0 volts to, say, the gate voltage that you're giving the MOSFET, and that's the plateau period. So that's why the charge of this MOSFET is important, because anytime you see a capacitance and you're trying to go from one state to another state, you can think of it as slowing down. And, there's an RC time constant. So think of the capacitance as the best way to look at it is that it's slowing down the switching time. So it cannot be instantaneous. There's that the amount of farad present in the capacitance is how long it's going to take before it reaches the state of fully on or fully off. And that's what we're trying to simulate over here and see, get those conditions. So if we go over here to PSM and if I see the gate, it's not quite really giving me the plateau in this particular graph. And that's something that I'm trying to figure out. How do I basically simulate the plateau, or maybe not part of the SPICE model, understanding the that plateau region basically. So that's something that I would want to really investigate more into, figuring out how I can understand and how I can simulate that. Another aspect is you can also look at the turn on time and the turn off time, the fall time and the rise time. Here we have the drain source voltage as 12 volts. Here we have a load of 0.6 amps, gate source voltage of 46 volts, 4.5 volts, and based on these conditions, it'll take 25.1 nanoseconds to turn on, and the rise time is 30.3 nanoseconds. So I'm not too sure if I can actually necessarily simulate this, but we can try. So if I go to a drain to source voltage of 12 volts, the RL is 0.6. So let me just go over here and click here 0.6. Just go here and put here 0.6. And we have a gate to source voltage of 4.5. Then you have an RG, which is the gate resistance of 5 ohms. Okay, so what they are asking over here is 4.5 ohms. So the maximum I'm going to put over here is 4.5. And that's one thing with simulations. I can look at a data sheet and then it says it needs another gate resistance. So I'm going to go over here and just put a gate resistance right in here. Connect this and then connect this to this. And the gate resistance is supposed to be 5 ohms. So I'm going to put this as 5. Perfect. And now let's run this and see what graph I'm supposed to get. I'm trying to simulate the turn on and turn off time over here. So let's have a look at the simulation result. And I should just directly go to the gate voltage over here. And if we zoom in, I'm not too sure if I can zoom in here. So we're going from, yeah, this is where the graph is basically, I mean, even if I keep zooming in, it's like, yeah, I mean, this, like, because it's in nanoseconds, like, well, we're trying to deal over here with nanoseconds. We're expecting this to basically have a 24.1 nanoseconds and 30.3 nanoseconds, and my period is in like 1 second. So it's going to be so small. So I need to really zoom in. MATLAB may not be the, maybe we could try to change the thing to like 50 nanoseconds. Let me try a sample time. Derivative. So let's go to sim, and I'm just gonna put this in. Let's put it super small. T simulation will be, here I put it as 1 second. Here I'm gonna put this as, say, 100 nanoseconds. So I'm just gonna put this as, and this will open this big cell. Let's put this as 100 e raised to -9. Let's see what happens. And then, so that should accommodate, at least we should be able to see the rise time. and that should be super quick. And then let's go and explore. So this will be more like a transient condition. And then let's go to the gate. Yeah, it doesn't even show you, does it? And it doesn't show me because this itself is taking, my rise time over here is 1 nanosecond. Yeah, it should be here. I can put this as -9, maybe -12, I don't know. Yeah, this should work. Consistency tolerance, oh yeah, because we're sampling it at, so I'm just going to put 1 e raised to -15 or -9. Yeah, so 1 every 1. Hopefully this works. It'll take a while. So we have 3 warnings. Let's see what the 3 warnings are. Time on one or more assertions are triggered, large value and set exponential. Yeah, let's see if this works. So when it comes to transient analysis, MATLAB may not be the best tool, and that's one way of also, is are you using the right tool for, yeah, here we go, like it is starting to simulate. So if we go to gate, so it's 0 and it's going negative. So this is not making too much sense, is it? So it's 12 volts, which is already on, and here we have it at, so it's going to 0 and it's going to -50. I don't know what that is. And here we have a source to 10. So the transient analysis is not making too much sense to me. Resistance at the gate. Let's look at the resistance, just normal resistance over here. So this is the gate resistance, and the current that is flowing through is here. So this is telling me what's happening at the gate resistance. So let's turn this to 0 ohms then, just to see what happens, because it's slowing this down and it's basically causing some form of resistance must be greater than 0. Okay, 0.01. Let's put this super small. Run this, and now let's look at the simulation results. I got so many windows open. It's turning out to be a long video, but the whole idea over here is, like, if you can get the MOSFET from the data sheet, get the SPICE model and simulate based on the actual characteristics of this, and just play around with the parameters to get a sense and intuition of whether this MOSFET is right for you, is one way to basically select the MOSFET. And here we have it. Yes, it's going to 0.5 volts. It's yeah, the transient analysis is not perfect, I would say. Like, I'm not seeing the plateau region, I'm not seeing the Miller effect, basically. The source is, yeah, like, there are many things that I'm not too sure whether MATLAB is able to, or the SPICE model is able to capture right now. And that's something, you could analyze and say whether this is the right tool, or maybe it's not the right tool to understand those more important, or rather more what do you say, specific characteristics of a MOSFET that are more advanced characteristics of a MOSFET that may or may not be of interest to you. Anyways, so that's what this video was all about, is to basically simulate a MOSFET using any simulation tool. And the process is simple, is very straightforward. Choose a MOSFET that you want to use. In this particular case, I'm using the PSM one from here. You go to the data sheet. You can also go to the manufacturer, and then they will give you the they'll give you the SPICE model that you could download. Where do I have that over here? So yeah, you can go to the manufacturer, look at all the data that they're giving you, look at the manufacturers, whether they're giving you a SPICE model, and look at the data sheet, see if it makes sense to you, and from there see whether an application, whether this MOSFET fits the application that you're working with. And it's really, I personally believe it's a great way to really dive deep into the components when you're working with, say, a drone or any sophisticated robot, and really building things up, because a lot of these things you buy straight from hobby shops, and they just somehow work for you, but they may not be the best tool for the drone that you are designing. And you really can't be too creative if you buy something off the shelf, because now it might be very optimized for a very specific configuration, and if you change that configuration, and if you don't want to use a quadcopter, you want to use, say, a bicopter or a helicopter, it may not necessarily fit your needs. And you also want to make sure that the propellers that you're mounting onto the ESC, it works with your ESC. And for it to work with your ESC, you need to know whether your MOSFET can handle it. So really understanding some of the components that you're selecting to make sense of it, simulating to see whether it'll handle the current, the voltage that you're really going to subject it to, is a great way to really build things from the grounds up. And that's all that I have for you right now. And until next time, take care.